Module 3, Lecture B, Saving and Loading. By the end of this lecture, you will be able to save and load arrays using NumPy-specific formats such as .NPY and .NPZ with appropriate options. Import and export array data from text-based formats like CSV while controlling dtypes and delimiters, and integrate NumPy arrays with external tools by converting to and from common formats such as Python buffers and memory-mapped files. NumPy file formats. Saving and loading arrays. In scientific projects, it is important not only to compute numerical results, but also to store them so they can be perfectly restored later. NumPy provides a binary file format that preserves an array's shape, data type, and values. This allows you to save the exact state of an array, close your program, and reload it later without any loss or change. Such reliable saving and loading is especially useful when the data comes from expensive processes like simulations or model training. NumPy's binary format makes saving and loading arrays simple and reliable. When you save an array this way, the file stores both the raw data and key details such as its shape and data type. As a result, when you load the file, the array is recreated exactly as it was, without needing to remember its dimensions or type. This avoids the formatting problems of text files and preserves structure and precision, even for complex data like three-dimensional temperature grids. Using NumPy's binary format to save arrays makes data workflows more stable and reliable over time, which is especially important in long-term projects such as climate science and finance. This format keeps the array representation consistent across different systems regardless of local settings like decimal separators or text encodings. As a result, teams can safely store and share intermediate results between steps like pre-processing and modeling. Knowing that each stage will receive exactly the data it expects without conversion errors. Python code, saving and loading arrays. This section shows how to save NumPy arrays to disk using the NPY file format, then load them back into memory. The goal is to demonstrate that when you reload the saved arrays, both their shapes and their numerical values are preserved exactly. By comparing the original and reloaded arrays, you can confirm that the data has not changed during the save and load process. This verifies that the NPY format is a reliable way to store and restore NumPy arrays without any loss of information. In this script, we use NumPy, a Python library designed for efficient numerical computing. NumPy works with large, multi-dimensional arrays and matrices and provides many mathematical tools to process them. Here, it will help us handle numerical data and perform operations needed to save and load arrays in a fast and convenient way. We begin by creating an array of temperature values in Fahrenheit using a numerical computing library. This array holds 4 floating point numbers, each representing a different temperature reading. Using this library makes it easy and efficient to store, handle, and manipulate these numerical values. It also prepares the data for later tasks, such as saving the temperatures or performing further processing on them. We use the NumPy save function to write the temperature array to a file on disk in a special binary format. This format is specific to NumPy and preserves the array's exact structure and values. The file is named dailytemps.npy to indicate that it is a NumPy file. Using this format makes it easy to reload the data later with the same precision and shape. This code loads a previously saved NumPy array from a file called dailytemps. It uses the NumPy load function to read the binary file and rebuild the array exactly as it was stored. Both the data values and the array's shape are preserved. This allows you to quickly retrieve the original data without losing any information. We first display the original temperature array, including its values and shape, to verify the data before saving it. After saving and then loading the array from a file, we print the loaded version in the same way. By comparing the values and shapes of the original and loaded arrays, we confirm that the data has not changed. This check ensures the saving and loading process preserves the integrity of the data. We print the loaded temperatures array to check that it was saved and restored correctly. By looking at its values and its shape, we confirm that the data from the file matches the original array. Verifying the shape shows that the dimensions are preserved. This demonstrates that using NumPy's binary format reliably maintains both the data and its structure during the save and load process. This script shows how to save and load arrays using the binary format provided by the numerical Python library. It creates an array of temperature values in Fahrenheit and saves it to a file so that its structure and data are preserved. The script then loads the array back from the file and prints both the original and the loaded versions. By comparing them and seeing that their shapes and values match exactly, it confirms that the save and load functions maintain the integrity of the data. Comparing NPY and NPZ. In NumPy, NPY and NPZ are different file formats used to store arrays. An NPY file stores a single array along with its metadata, so it is well suited for one dataset, such as a large image or a time series. An NPZ file is a container that bundles several NPY arrays together, and each array inside has its own name. In practice, you can think of NPY as a format for one labeled array and NPZ as a way to group multiple related arrays from the same project into one file. Choose between NPY and NPZ based on how your data is organized and how you plan to use it. If you mainly work with a single large array, such as a matrix for machine learning, saving it as an NPY file is simple and efficient. If you need to store several related arrays together, like user features and labels in a recommendation system, an NPZ archive is better. It keeps all arrays in one file, preserves their names, and helps keep your data organized and easy to manage. When choosing between NPY and NPZ formats, focus on performance and how you want to organize your data. NPY stores a single array and is faster to read and write, so it works well for quick checkpoints in simulations or training loops. NPZ bundles multiple arrays into one file, making it convenient for sharing structured datasets and accessing each part by name. In short, use NPY for simple, single array storage and NPZ for organized collections of related arrays. Python code comparing NPY and NPZ. This lesson shows how to save a single array using the NPY format, then how to save several related arrays together using the NPZ format. It explains that NPY is useful when you only need to store one array. while NPZ is better for grouping multiple arrays in one file. Finally, it compares how to load data from NPY and NPZ files and suggests printing simple summaries so you can clearly see the differences in how the saved arrays are accessed. We begin by importing the numerical computing library NumPy to efficiently work with arrays and other numerical data. We also import the path class from the pathlib module, which gives us a convenient way to handle file system paths using objects instead of plain text strings. Together, these imports prepare the tools we need for managing both numerical computations and file locations in the rest of the code. We begin by setting up two simple arrays to store daily weather data. One array holds temperature values in Fahrenheit, using a 32-bit floating point type for efficient storage and computation. The other array stores humidity values as 32-bit integers to keep the data compact while still accurate. These arrays will later serve as basic examples for how to save and load data in different formats. We use the NumPy save function when we want to store a single main dataset efficiently. In this example, we save an array of daily temperatures called temperatures in Fahrenheit into a file named dailytemperatures.npy. This file format is designed for storing one array and makes it easy to load that data back into a program later. Overall, it is a simple and effective way to preserve a single array for future use. In this example, we store several related arrays together using a NumPy NPZ archive so they are kept in a single file. We call the NumPy saveZ function, give the file a name like weather data, and then pass in each array as a keyword argument. Each array is given a clear label, such as tempsF for temperature data and humidity for humidity data. Using these names lets us easily retrieve each specific array when we load the NPZ file later. We load a previously saved array from a file using the NumPy load function, which reads data stored in the NPY format designed for a single array. After loading, we immediately check the array's shape and data type by accessing its shape and data type attributes. Printing these values lets us confirm that the array was loaded correctly and that its structure and data type match what we expect. To work with data stored in an NPZ file, we load it using the NumPy load function, which lets us treat the archive like a dictionary where each stored array can be accessed by its name. After loading, we print the available keys to see the names of all arrays contained in the file. This quick check tells us what datasets are present and how we can refer to them in our code. Understanding these keys is essential for correctly accessing and using the data in the archive. We load specific arrays from the NPZ archive by using their stored names, first accessing the temperature data and then the humidity data. After loading them, we quickly check that the temperature array was read correctly by printing its first value and the total number of elements it contains. This simple summary confirms that the data has been successfully retrieved from the NPZ file and is ready for further use. This line shows how to read and display specific data stored in an NPZ file by printing the first humidity value and the total number of humidity entries. Doing this confirms that humidity data is present and correctly stored in the same NPZ archive as the temperature data. It demonstrates that related datasets can be efficiently retrieved and inspected together from a single compressed file. The code verifies that the previously saved data files are actually present on the disk. It uses a file path utility to check whether the NPY file containing daily temperatures and the NPZ file containing the combined weather data archive exist. The program then prints the results of these checks. This confirms that the data has been successfully stored in both a single dataset file and a combined archive file. This script shows how to save and load data using NumPy's NPY and NPZ formats. It creates temperature and humidity arrays, saves the temperature data alone in an NPY file, and then saves both arrays together in an NPZ file that works like a named collection of datasets. When the files are loaded, you can inspect the shape and data type of the temperature array, list the keys stored in the NPZ archive, and access each array by its name. The script also confirms that both files exist on disk, illustrating the difference between storing data in separate files and in a single combined archive. Compressed archives with save as. NumPy's compressed archive format is useful when you need to store several arrays in a single file. It bundles the arrays together and compresses them, which saves disk space and is helpful for large datasets. Each array is stored with a name, and when you load the file, you get a dictionary-like object that lets you access each array by its name. This keeps multiple arrays organized and easy to manage in one place. Compressed archives trade CPU time for smaller file size. They reduce storage use and speed up network transfers, which is especially useful in cloud environments. This is a good choice for large datasets that are accessed rarely, such as archived results or shared data. However, because compression and decompression take extra processing time, uncompressed formats are usually better when you need to read and write the same data frequently in performance-critical loops. Compressed archives help organize complex projects and make them easy to reproduce. They let teams bundle related elements, such as data, features, model settings, and results, into a single file that captures the exact state of an experiment or analysis. In fields like climate science or education, arrays can be grouped and clearly labeled, so they are easy to access, share, and reuse on different systems. Overall, this approach supports better organization, consistent sharing, and reliable reconstruction of workflows from one archive. Python code, compressed archives with save ves. Use the compressed save feature in NumPy to store several arrays together in a single archive file, assigning each array a clear, descriptive name. This approach lets you compare the smaller compressed file size with the larger uncompressed data size, making the trade-off between storage space and raw data clear. When you load the archive later, you can easily access each array by the name you originally chose, allowing organized and efficient retrieval of your saved data. We begin by importing two key tools for our script. First, we load NumPy, a numerical computing library that lets us work efficiently with arrays and perform fast mathematical operations. Then we import the operating system module, which allows the script to interact with the computer's file system, such as checking file sizes. With these imports in place, we are prepared to save and load data and compare the sizes of the resulting files. We begin by creating two NumPy arrays that store daily temperatures in Fahrenheit for two different cities. One array holds values for city A, such as 70 and 72.5 degrees, and the other array holds values for city B, such as 60 and 62 degrees. These temperature arrays will serve as simple example data that we can later use to demonstrate how NumPy saves and compresses information. We store the temperature data for city A by using a save function that writes the array to an uncompressed file called cityatemps.npy. We repeat this process for city B, saving its temperatures to a separate uncompressed file called citybtemps.npy. Because these files are uncompressed, they keep the data in its original size. Later, we can compare the sizes of these separate files with a compressed archive to show how compression improves storage efficiency. We use the compressed save function from NumPy to store both arrays together in a single file, which creates a space-efficient archive. The file is named temps archive with an NPZ extension. Inside this archive, we assign the first array to a key called ACity and the second array to a key called BCity. Using these named keys makes it easy to retrieve each array later and keeps the data organized and efficient to store. The code demonstrates space savings from compression by comparing file sizes. It first gets the size of the uncompressed temperature data for city A and city B using the operating system's file size function. Then it retrieves the size of the compressed archive that contains both cities' data. By comparing these values, it shows how much storage space is saved when the data is compressed into a single archive. The code first calculates and prints the combined size of the two original files in bytes to show how much space they use when stored separately. It then prints the size of the single compressed archive that contains those files. Comparing these two values makes it easy to see how much space is saved by compression and the trade-off between storing files individually and storing them together in a compressed form. We begin by loading the compressed archive file with a NumPy loading function, which gives us an object that works like a dictionary of stored arrays. Each array in this archive can then be accessed using the name it was originally saved with. To check what data is available, we print the list of keys from the loaded archive. This confirms that the data has been loaded correctly and shows us the names we can use to retrieve each array. We first print the temperatures for city A that were loaded from the compressed archive, showing how to access a specific array using the name it was saved with. We then do the same for city B, again retrieving its temperatures by the assigned name. This illustrates how using clear, descriptive keys makes it easy to pull out exactly the data you need from a compressed archive. This script shows how to save and compress multiple arrays using NumPy's compressed archive feature. It creates two arrays of daily temperatures for two cities, first saving them separately in an uncompressed form, then together in a single compressed file. The script compares the total size of the uncompressed files with the compressed archive to demonstrate how much storage space is saved. Finally, it reloads the compressed archive, retrieves the arrays by their assigned names, and confirms that the data remains intact and accessible, illustrating an efficient way to store and manage multiple datasets in one file. Text data loading. Loading text files. When working with numerical data stored as plain text, such as CSV files or instrument logs, the key goal is to load the values into an array for analysis. This means not just reading characters, but correctly interpreting them as numbers and arranging them into rows and columns. To do this, you must understand the file structure, including whether it has a header row, how many columns to expect, and how comments or missing entries are marked. For example, a public health dataset may begin with descriptive lines and a header before the actual data. So you need to configure your tools to skip those lines and convert only the true data into a clean, consistent numerical array. When loading text files into arrays, each line usually becomes a row, and each value in that line becomes an element in that row. To make this work correctly, you must use the same delimiter the file uses, such as a comma or a tab. If the file uses commas, but the loading process expects spaces, the data will not split into proper columns, and the array may be unusable. By matching the loading settings to the file's structure, each column will represent a meaningful variable, which supports accurate slicing, aggregation, and visualization. When loading text files, you must account for messy real-world data, such as extra spaces, inconsistent numbers of columns, or non-numeric entries like error messages. For instance, a failed sensor might record the word error instead of a value. You need to choose whether to skip these lines, replace them with placeholders, or store them separately for later review. You also have to recognize and ignore headers or comments that are not actual data. Careful configuration of the loading process helps you filter out non-data elements. Protect data integrity and produce a clean array ready for analysis. Python code: loading text files. This section explains how to load simple numeric text data using the NumPy load text function. You see that each line in the text file becomes a row in the resulting array, and values separated by commas or spaces become columns. To make this concrete, you create a small comma-separated values file, load it with the function, and then print the array to observe how the text data is converted into a structured numeric format. We begin by importing the NumPy library, which lets us work efficiently with large, multi-dimensional arrays and matrices, and provides many mathematical functions for operating on them. We also import the path class from the pathlib module, which gives us an object-oriented way to handle file system paths. Using path makes it easier to create, read, and write files in a clear and intuitive way. We create a text string that holds a small set of data in comma-separated values format. The first line is a header that names the columns for date, temperature in degrees Fahrenheit, and humidity as a percentage. After the header, there are 3 lines, each giving a specific date along with its temperature and humidity values. This simple dataset is prepared so it can later be written to a file and used for demonstration. We start by creating a path object for our CSV file, giving it the name weatherdata.csv to specify where it will be saved. Then we write the CSV content into this file using a method that handles text, and we choose UTF-8 encoding so characters are stored correctly. Together, these steps create the CSV file in the working directory with the data we prepared earlier. We use a data loading function from NumPy to read values from a comma-separated file. The file location is given by a variable, and the delimiter is set to commas, so the function knows how to split the values. We skip the first row because it contains headers instead of data. We then load only the second and third columns, which hold the numeric temperature and humidity values, and ignore the date column. The result is a 2-dimensional array where each row contains 1 day's temperature and humidity. We print the loaded array to confirm that the numeric data was extracted correctly from the file. Each line in the file becomes a row in the array, and each comma-separated value becomes a column. This output lets us verify that the temperature and humidity values are in the expected positions. Checking this structure is an important step before doing any further processing or analysis. We check the shape of the data array to confirm its dimensions. This step verifies that the parsing worked correctly. In this case, the result shows 3 rows and 2 columns. These dimensions match the numeric temperature and humidity values that were extracted from the file. This script shows how to load numeric data from a CSV file using a NumPy function for reading text. It first creates a small CSV file with weather data, including a header and 3 rows of numbers, and saves it locally. The script then reads the file while skipping the header and selects the numeric columns for temperature and humidity. It prints these values as a 2-dimensional array and reports the array's shape, confirming that it has 3 rows and 2 columns, matching the original data. Handling missing text data. When working with text data files, such as CSVs, you will often encounter missing values, which may appear as empty fields or inconsistent markers like NA or null. These missing entries must be handled carefully because they influence how arrays are built, how data types are inferred, and how later analyses behave. If they are not correctly recognized when the data is loaded, they might be treated as strings, turned into zeros, or cause rows to be dropped, all of which can distort results. Therefore, it is essential to have a clear strategy for detecting and encoding missing data at load time so that arrays are reliable and later computations, such as statistical summaries or model fitting, remain valid. When working with missing text data, you first need to decide which patterns count as missing values and how they will be stored. Different datasets may use markers like NA, blank entries, or special numbers such as -9,999. As you load the data, convert all of these markers into a single consistent form, such as a special, not a number value, or a masked entry. This unified representation lets you safely compute statistics like means or correlations without being misled by placeholder values, while still preserving the structure of the original file and keeping your analysis clear. When working with data that has missing values, you need to think about how they affect data types and array structure. If a column in a CSV file is mostly numeric but has some missing entries, a basic loading method may treat the entire column as text, which makes numerical analysis harder. To avoid this, use flexible numeric types or masked arrays that can represent missing values while keeping the data numeric. Planning for missing data during loading helps preserve the integrity of datasets, such as climate records with missing temperature readings, and ensures your arrays are ready for accurate analysis. Python code, handling missing text data. This section focuses on using the NumPy genFromText function to load text data that contains missing values. It shows how different markers for missing entries in the raw text can be interpreted and converted into consistent not-a-number values inside NumPy arrays. The narration also compares what happens when you use genFromText with explicit options for missing values versus relying on its default behavior. Overall, the goal is to understand how genFromText standardizes various missing data indicators into a uniform representation for easier analysis. We begin by importing NumPy, a Python library that provides efficient tools for working with numerical data and arrays. It is widely used to perform fast mathematical operations. We also import string IO from the input-output module, which lets us create an in-memory file-like object from a string. This allows us to handle text data as if it were stored in a file, without actually creating a file on disk. We begin with a short text string that imitates a small CSV file containing 3 columns: day, temperature in Fahrenheit, and humidity. Each line represents one day, and some temperature values are missing in different ways. One row uses the marker NA, another leaves the temperature field empty, and another uses the value -9,999 to indicate missing data. This setup is used so we can later show how to treat all these different markers as missing values in a consistent way in the code. We wrap our comma-separated text data in a string IO object to simulate a real file, so we can use normal file-style operations on a string. This is especially helpful when working with tools that expect a file input, such as the genFromText function in NumPy. By treating the string as a file, we can load, read, and manipulate the data more easily, just as if it were stored in an actual file, which simplifies further processing and analysis. We load the text data using NumPy's genFromText function, which reads from a text file stored in a string IO object and uses commas to separate values. By telling it to treat the first line as a header, it automatically assigns names to the columns. And by leaving the data type and encoding unspecified, NumPy infers the types and uses the default system encoding. However, this basic loading step does not handle missing values, so any gaps or non-numeric entries in the data can lead to unexpected numeric results or errors in the resulting array. This line displays the raw data array that was loaded from the text file. The data has been read in directly without any special treatment for missing values. As a result, places where missing data markers appeared in the file may now show up as unexpected numeric values. Viewing this output helps us see the unprocessed state of the data before we apply any cleaning or pre-processing steps. Before reloading the text data with better missing value handling, we move the string IO object back to the start. This reset makes sure that the next read begins from the very beginning of the text. By doing this, we can apply new options for dealing with missing data correctly on the full data set. We reload the text data using a function that lets us control how missing values are handled. The data is read from a comma-separated text file, and the first row is kept as column names. We tell the function that entries written as NA as an empty string or as -9,999 should all be treated as missing. These different markers are then converted into a single standard value called nan, meaning not a number. This standardization cleans up inconsistencies in how missing data is recorded and makes the dataset easier to analyze. The code prints a cleaned data array that was loaded with a numerical data loading function. During loading, markers for missing values such as NA, empty entries, and the value -9,999 were all treated as missing data. These markers were replaced with special, not a number values. As a result, the dataset is now more consistent and better prepared for further analysis or processing. This script shows how to properly handle missing text data using the gen from text function in NumPy. It first loads a text file where missing values are marked in different ways, such as NA, blank entries, and the number -9,999. Without telling the function which markers represent missing data, these values are read as odd numbers and the data type may not be what you expect. The script then reloads the same file, but explicitly declares these markers as missing, so they are all converted to a consistent, not a number value. This produces a clean data array where missing entries are handled uniformly, making later analysis easier and more reliable. Controlling dtype and delimiter. When working with text data, such as CSV files, it is important to control how the text is converted into a structured array. You need to specify the delimiter because values might be separated by commas, tabs, semicolons, or other symbols, and guessing can lead to incorrect column splits. You also need to set data types explicitly, since leaving them to default can turn everything into strings or floats and distort values, such as turning precise IDs into imprecise numbers. By clearly defining both delimiters and data types, you preserve the correct structure and meaning of the data for analysis. When working with text files that contain different kinds of data, such as a clinical trial dataset, it is important to specify the data type for each column. For example, patient IDs should be stored as text, so leading zeros are not lost, while measurements like blood pressure should be stored as numbers. If you treat everything as text, you will have to convert numeric values by hand, which is inefficient. Defining data types explicitly preserves the accuracy of each column and improves memory efficiency, which matters especially for large datasets. When working with files from different sources, you must handle delimiters and data types carefully to avoid errors. For example, a European accounting file may use semicolons between fields and commas in decimal numbers, so using a comma as the delimiter would break numeric parsing. Instead, you should set the delimiter to a semicolon and specify that numeric columns use a floating point type. This ensures the raw text is interpreted correctly and converted into reliable arrays for analysis. Python code, controlling dtype and delimiter. In this section, you will see how to load text data while controlling custom delimiters, and how different data type choices affect how each column is interpreted. The focus is on demonstrating how delimiter settings change the way text is split into columns. You will also explore how specifying data types can alter the meaning and handling of those columns. Simple, small CSV examples are used so everything runs quickly and clearly in a Colab environment. We begin by importing NumPy, a common library used for fast numerical calculations and efficient handling of arrays. We also import the string IO tool from the input-output module, which lets us treat a string as if it were a file. This is useful when we want to perform file-like operations entirely in memory, instead of working with actual files stored on disk. We begin with a simple text string that represents our example dataset, where semicolons separate the different fields. Each line in this string acts like a row in a table, and each row contains an identifier, a temperature value, a distance value, and a status indicator. This structure gives us a small, organized dataset that we can later load, manipulate, and analyze using numerical tools such as NumPy. We start by turning the string of text data into something that behaves like a file using a tool called string IO. This lets us handle the string as if it were an actual file on disk. Doing this is important because it allows us to use NumPy's standard loading functions, which are designed to read from files, to process the text data stored in the string without any extra complications. In this example, NumPy is used to load text data from a file-like source, but the delimiter is incorrectly set to a comma. Because the actual data is not comma separated, NumPy treats each entire line as one long string instead of splitting it into separate columns. With the data type set to string, every line becomes a single string entry in the resulting array. This shows how choosing the wrong delimiter can break data parsing and produce an incorrect data structure. The code moves the file-like object back to the beginning so the data can be read again correctly. The earlier attempt to load the data with the wrong delimiter pushed the read position to the end of the file. By resetting the position, the next load starts from the beginning. This allows the data to be parsed properly using the intended delimiter and data types. We use a data loading function from NumPy with a semicolon as the delimiter, so the columns are split correctly. Each column is given a specific data type to ensure proper interpretation. The first column is an ID stored as a short string. The second is temperature in Fahrenheit, stored as a floating point number. The third is distance in miles, also stored as a float. And the last is a status stored as a short string. Defining these types creates a structured array where each column has the right format, making later data manipulation and analysis more accurate and reliable. This example shows what happens when text data is loaded with the wrong delimiter. Because the delimiter is incorrect, the program reads each entire line as one long string, instead of separating it into columns. As a result, all the columns are merged together. This clearly demonstrates why it is important to specify the correct delimiter when loading data. We now display the structured array that was loaded using the correct delimiter and specified data types. This output shows that the text data has been correctly split into separate fields, such as string fields for IDs and statuses, and numeric fields for temperatures and distances. Seeing the data in this structured form emphasizes how important it is to choose the right delimiter and data types when loading text data into a structured array. This script shows how delimiters and data types affect loading text data with NumPy. When a semicolon-separated string is read using a comma as the delimiter, the entire row is incorrectly treated as one long string. After resetting the input and using the correct semicolon delimiter, the data is properly split into columns. By also specifying data types for each column, such as strings for identifiers and status, and floats for temperature and distance, NumPy creates a structured array. The comparison makes clear that choosing the right delimiter and data types is essential for accurate data parsing. Advanced NumPy I/O Memory-Mapped Arrays. Memory-mapped arrays let you treat a file on disk like a NumPy array, while only loading the needed parts into memory. This allows you to work with datasets that are much larger than your available RAM, using familiar operations such as indexing and slicing. You still benefit from NumPy's powerful tools while efficiently handling massive data. When using memory-mapped arrays, you must ensure the file's layout on disk matches how you view it in memory, including the file location, data type, shape, and access mode. NumPy does not store extra metadata, so anyone sharing the file must also share its data type and dimensions to map it correctly. After mapping, you can work with the array like a normal one, but random access may increase disk activity, and changes are written back to the file according to the operating system's buffering. This approach provides a live view of the file, closely integrating computation with storage. Memory-mapped arrays let NumPy work efficiently with very large datasets and external tools. By treating data stored in files as if it were in regular arrays, without loading everything into memory. For example, a program in another language can keep writing data to a file while a Python script reads and analyzes it through a memory-mapped array. In machine learning, you can pre-process data into a large memory-mapped file that multiple scripts can access at the same time, saving both time and memory. Because the format is simple and portable, you can design high-performance storage that works across different environments while still using familiar NumPy operations. Python code, memory-mapped arrays. This section explains how to safely create and use NumPy memory-mapped arrays so you can read from and write to large files without loading them entirely into memory. It focuses on demonstrating how to access only the needed parts of the data while keeping the rest on disk. This approach is especially useful when working with very large datasets, such as long time series or high-resolution images that would not fit comfortably in main memory. We begin by importing the numerical computing library that lets us work efficiently with large, multi-dimensional arrays and matrices, and provides many mathematical functions for operating on them. We also import the operating system module, which lets our program interact with the underlying system in a way that works across different platforms. This is especially useful for managing file paths and performing file operations in a consistent, system-independent way. The code creates a file path for storing data by combining the current working directory with a specific data file name. This approach makes sure the file is saved in a consistent and expected location. As a result, it helps avoid problems that can occur when file paths differ across environments or user settings. Overall, it provides a safe and predictable place to store the sensor data file. To model hourly temperature data, we first calculate how many hours are in 1 year by multiplying 24 hours per day by 365 days. This gives the total number of hourly data points for a single year. We then choose how many years to simulate, in this case, 10. Using these values, we can build a large array that represents hourly temperatures over an entire decade, allowing us to work efficiently with a long time series of data. NumPy's memory map feature lets us create an array that is stored on disk instead of fully in memory, which is helpful for working with large datasets efficiently. We choose a file name to hold the data, set the data type to 32-bit floating point to save space, and open the file in a mode that allows both reading and writing. We then define the array's shape using the number of years and the number of hours per year, forming a two-dimensional structure that represents the dataset. We fill the first year of our memory-mapped array with a simple pattern that represents rising daily temperatures. To do this, we loop over each day of the week and compute the start index for that day by multiplying the day number by 24, then define the end index by adding 24. This gives us a specific range of positions in the array for each day. Within each range, we can then store the temperature values for that particular day. This line fills one day of the first year in the memory-mapped array with a smooth temperature pattern. It uses the linspace function from NumPy to create 24 evenly spaced temperature values that start at 60 and end at 80 degrees Fahrenheit, representing a gradual rise over the day. These generated values are then written into the array slice defined by the start and end indices for that specific day. We first flush the changes to disk so that all modifications made to the memory-mapped array are safely written to the file, which is essential for data integrity with large data sets. After that, we delete the reference to the memory-mapped array to release its associated resources. This step frees file handles in memory, supporting efficient resource use and helping prevent memory leaks. We reopen the file as a memory-mapped array in read-only mode, so we can analyze the data without loading the entire file into memory, which is especially efficient for large data sets. We set the data type to 32-bit floating point values to match how the data was originally written. We also specify the shape to represent 10 years of hourly data, so the array layout matches the original storage structure and the data can be accessed correctly. We begin by selecting the first week of data from the memory-mapped array, which corresponds to the first 7 days and their 24 hourly values. Next, we use the mean function from the numerical library to efficiently compute the average temperature over this selected week. Finally, we convert the resulting value into a standard floating point number, so it is easier to work with and display. We begin by checking the shape of the first week's data from the memory-mapped array to confirm that it behaves like a normal NumPy array, even though it is stored on disk. Then we compute and print the average temperature for that week, rounding the result to 2 decimal places. This illustrates that we can run standard numerical operations on memory-mapped data just as we would on regular in-memory arrays. After creating a temporary file, the code cleans up by deleting it using the operating system's remove function, which erases the file from the current working directory. This prevents leftover files from building up over time. Such cleanup is especially important in shared or limited environments like Colab, where unnecessary files can quickly consume available storage space. This script shows how to use NumPy memory-mapped arrays to work with large data sets without loading everything into RAM. It creates a file-backed array that represents hourly temperature data over 10 years and writes a simple pattern of rising temperatures for the first week. The data is flushed to disk. The file is closed and then reopened in read-only mode to compute the average temperature for that first week using vectorized operations. Just as with a normal NumPy array, the script prints the shape of the week's data and the average temperature, then deletes the file to clean up, demonstrating efficient, file-based numerical analysis. Buffer-based interactions. Buffer-based interactions let NumPy arrays expose their raw bytes in memory, so they can connect efficiently with other Python tools. By treating an array as a simple block of bytes, its data can be shared or streamed without copying and used directly by objects like byte arrays, memory views, compression libraries, or binary parsers. This reduces overhead and avoids repeated allocations. For example, when binary data arrives over a socket and is interpreted as a buffer that is immediately wrapped in a NumPy array for fast processing. Buffer-based interactions allow NumPy arrays to integrate smoothly with systems that work directly with raw binary data, such as C extensions or GPU interfaces. These systems typically expect contiguous memory, and by exposing a NumPy array as a buffer, they can access its memory directly without copying. This enables zero-copy workflows where the same data is shared between NumPy and low-level components. For example, in real-time signal processing, incoming binary sensor data can be exposed as a buffer wrapped by NumPy as an array for analysis and simultaneously shared with device drivers or C libraries. Buffer-based interactions let you handle compact binary data efficiently by mapping a defined binary layout directly onto NumPy arrays instead of using high-level serialization. This is especially useful in areas like financial trading, where tick data is stored as binary records. By memory mapping these bytes into buffers, Python can treat them as NumPy arrays and manipulate them quickly without extra conversion steps. Although this requires careful attention to data alignment and byte order, it enables very fast pipelines that connect Python smoothly with native libraries and storage systems. Python code, buffer-based interactions. This material explains how NumPy arrays can share their data using the Python buffer protocol. It shows how to convert an array to a sequence of bytes and then reconstruct the array from those bytes without making extra copies of the data. It also illustrates how a memory view can be used to access and modify the shared underlying buffer, so that changes through the memory view are reflected in the original NumPy array. Overall, the focus is on efficient data sharing and in-place modification rather than duplicating array contents. We begin by importing the numerical computing library, NumPy, which is essential for working with arrays and performing fast numerical calculations in Python. This library supplies the core tools needed to manage data in array form. It also supports the buffer-based interactions that the script will demonstrate. In short, NumPy provides the foundational functionality that makes the rest of the code possible. We create a NumPy array to store temperature values in Fahrenheit using the float32 data type. The array is initialized with the values 32, 68, 77, and 104. Using float32 controls the precision of each value and helps with memory efficiency. It also keeps the data compatible with other operations that expect this specific numeric type. A memory view of a NumPy array gives direct access to the raw bytes that store the array's data. It lets you work with the array's underlying buffer without making a separate copy. This makes data manipulation and sharing more efficient because operations can be done directly on the existing memory. We convert the memory view of the NumPy array into an immutable bytes object so the data can be safely sent or saved. Using bytes provides a standard format that many systems and tools can handle. This conversion helps ensure the data is transmitted or stored without changing its original structure. We can rebuild a NumPy array directly from a raw bytes buffer by using the FromBuffer method and specifying the data type as 32-bit floating point. This creates a new array that points to the same underlying byte data instead of copying it. Because no extra copy is made, this method is more efficient and uses the buffer protocol to access the original bytes directly. We create a writable memory view of the original NumPy array so we can modify its data directly. This means we work with the same underlying memory instead of making a separate copy. As a result, any changes we make through this view update the array in place. This approach is more efficient for both memory usage and performance. We begin by getting a writable memory view of the original array so we can change its underlying data directly. Then, we create a new NumPy array holding the value 212 as a 32-bit floating point number and convert it to raw bytes. By writing these bytes into the first 4 bytes of the memory view, we overwrite the first element of the original array. This changes that value to 212 Fahrenheit and shows how memory views let us manipulate the shared data buffer directly. We print the modified NumPy array to show that changing the shared memory buffer through a writable memory view directly updates the array's contents. This demonstrates that the array and the memory view refer to the same underlying data. As a result, any changes made through the memory view are immediately visible when we inspect the original array. The code prints an array that has been rebuilt from a bytes buffer, showing that this reconstructed array is a completely separate copy. Any later changes to the original array do not affect this new one. This behavior illustrates how the buffer protocol can be used to create an independent instance from raw bytes, ensuring that modifications to the original data leave the reconstructed version unchanged. This script shows how the Python buffer protocol works with NumPy arrays to handle data efficiently. It starts with an array of Fahrenheit temperatures, exposes its raw bytes through a memory view, and converts them into an immutable bytes object that can be sent or saved without extra copying. A new NumPy array is then reconstructed from these bytes, demonstrating that the original data can be recovered. The script also creates a writable memory view on the original array so that changing a value, such as setting the first temperature to 212 degrees, directly updates the shared buffer. The reconstructed array from the bytes does not change, showing that it is an independent copy, while the original array reflects the modification, highlighting the efficiency and flexibility of memory views and the buffer protocol in NumPy. Efficient large array storage. When working with large arrays, it is important to store them efficiently so they use less disk space while still allowing fast access. This requires balancing space savings, performance, and compatibility with other tools. Some users may prefer compressed storage to reduce costs even if reading is slower, while others may accept larger files to gain speed. The best choice of storage format and strategy depends on how often the data is accessed, how it will be processed, and what other systems need to use it. To store large arrays efficiently, it helps to separate their logical structure from how they are laid out in memory and optimize that layout for the hardware. By placing array data contiguously and in predictable patterns, the system can stream large chunks that match disk blocks and cache behavior. This makes it possible to read only the needed parts without rebuilding the whole dataset. which is especially important in applications like medical imaging that require fast access to specific slices. Aligning storage with typical access patterns reduces disk traffic and memory usage, and this becomes even more critical when many users or processes are working with the data at the same time. Efficient storage for large arrays should support data that grows and changes over time without forcing you to rewrite everything. You need formats that let you append new data, read only the parts you need, and work smoothly with tools like databases. For example, time-partitioned files for sensor data allow fast writes and selective loading. This strategy controls storage costs, avoids expensive rewrites of large files, and keeps the data usable across different systems without costly conversions. Python code, efficient large array storage. This section explains how to store large arrays efficiently using NumPy's binary formats. It compares saving data as one large file with saving it as several smaller, chunked files. The key idea is that chunked storage lets you load only the specific parts of the data you need, instead of reading the entire array into memory. This makes working with very large datasets more efficient and scalable. We begin by importing the numerical computing library that lets us work efficiently with large, multidimensional arrays and matrices, along with many mathematical functions we will need for handling big datasets. We also import the operating system module, which lets our program interact with the computer's file system. This is important for tasks such as checking file sizes and managing file locations when storing and retrieving data. To simulate hourly temperature data in Fahrenheit over 5 years, we first find the total number of days by multiplying 365 by 5, and note that each day has 24 hours. We then use a random uniform function from a numerical library to generate temperature values between 50 and 100 degrees. The total number of values is the number of days times the number of hours per day. These values are arranged in a two-dimensional array, where each row represents a day and each column represents an hour of that day. To find how much memory a large array uses, we first read its attribute that reports the total number of bytes it occupies. We then convert this value to megabytes by dividing by the number of bytes in 1 megabyte. Finally, we print the approximate size of the array in megabytes, rounding the result to 2 decimal places for easier interpretation. We first save the entire large array into a single file using NumPy's save function, which stores it in an efficient binary format on disk. Then we use the operating system's function for getting file size to find out how many bytes this file occupies. We convert this value to megabytes by dividing by the appropriate factor and print the result. This process lets us estimate how much storage is required when we save the whole dataset as one large file. We divide a large dataset into yearly chunks by first choosing the number of years, then computing how many rows of data belong to each year based on the total number of days. For each year, we calculate the starting and ending row indices, slice out that portion of the array, and treat it as that year's data. We then create a year-specific file name and save each chunk as a separate NumPy binary file. This organization lets us efficiently store the data and later load only the year we need. We load data for a single year from the chunked files using a function that reads only the needed portion, so we avoid loading the entire dataset into memory. From this subset, we compute the mean temperature for the third year by applying a built-in averaging method. We then report this mean temperature, rounded to 2 decimal places, for clarity. This process shows how chunked storage supports efficient work with large datasets by allowing targeted access and calculation on just the relevant data. We load the full temperature dataset from the file using the NumPy load function so all the data is available in memory. Then, we compute the average temperature across all recorded years by calling the mean operation on this array. Finally, we display this overall mean temperature rounded to 2 decimal places to clearly summarize the long-term temperature pattern. This example shows how chunked storage lets you load only the data you need, rather than the entire dataset. It reports how many rows are loaded from a single year's file, illustrating that you can work with just that subset. This approach is more efficient and is especially useful in workflows where you only need specific portions of a large dataset. This script shows how to efficiently store and load large arrays with NumPy using a synthetic dataset of hourly temperatures over 5 years. It compares the memory size of the full array with its size when saved as a single binary file, then splits the data into separate yearly files. By loading only the third year to compute its mean temperature, and then reloading the full dataset to find the global mean, it illustrates how chunked storage allows smaller, targeted reads. The example confirms the number of rows in a single year's file, highlighting the efficiency of working with only the data you need instead of the entire dataset at once. In this lecture, you learned to save and load arrays using NumPy-specific formats such as .NPY and .NPZ with appropriate options. Import and export array data from text-based formats like CSV while controlling dtypes and delimiters. And integrate NumPy arrays with external tools by converting to and from common formats such as Python buffers and memory-mapped files. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.